Welcome to the session on solution of nonlinear equations using numerical methods. In applied mathematics, a frequently occurring problem is to find one or more roots of equations of the form f of x equal to 0. If f of x is quadratic, cubic or a biquadratic expression, the roots may be evaluated using the available algebraic formulae. But it is very difficult to find the roots if f of x is a polynomial of higher degree or f of x contains transcendental functions like e raised to x, sin x, log x, etc. In such situations, we can find the roots by approximation methods. Here, we shall discuss some of the commonly used numerical methods to find the roots of the equations of the form f of x equal to 0, where f of x may be algebraic, f of x contains transcendental functions, or f of x is a combination of both. All the methods are based on the important property of a continuous function. That is, if f of x is a continuous function on an interval a b, such that f of a and f of b are of opposite signs, then there exists at least one root of the equation f of x equal to 0 in this interval a b. This theorem or this property may be known as the location theorem. The first method is bisection method. This is a simple method to solve such type of equation f of x equal to 0. In this method, we find two numbers. By the location theorem, we find two numbers a and b such that f of a and f of b are of opposite signs. For convenience, we assume that f of a is positive and f of b is negative. Now, we bisect the interval a b, that is x naught equal to a plus b divided by 2, which may be taken as the approximate root of the equation f of x equal to 0. That is, we can take first approximate value of the exact root as this bisected value x naught. Now, we evaluate f of x naught. If f of x naught equal to 0, then x naught is the exact solution. Otherwise, f of x naught may be positive or negative. Assume f of x naught is positive. Then we take the interval of approximation as x naught comma b, because f of a is greater than 0, that is f of a is positive and f of b is negative in the first iteration. Now, we got f of x naught is positive. That means f of b is negative and f of x naught is positive. Therefore, by the location theorem, there exists a root in between x naught and b. Now, we bisect this interval again, which may be taken as x1, that is equal to x naught plus b divided by 2, which may be taken as the next approximate value of the exact root. Now, we evaluate f of x naught. If f of x naught is equal to 0, then then x1 is the exact root. Otherwise, we find the next interval of approximation depending on the sign of f of x1. Continue in this manner. In a finite number of steps, we get the approximate value of the exact solution. This is the method, that is method of bisection. Now, we have to work out a problem. The problem is find a real root of the equation 3x square plus 5x minus 40 is equal to 0, which is of the form f of x equal to 0, where f of x equal to 3x square plus 5x minus 40. Now, we will find out an interval of the form interval a b, where f of a and f of b are of opposite signs. If x equal to 0, we get f of 0 equal to minus 40, which is negative. F of 1 equal to 3 into 1 square plus 5 into 1 minus 40, which is again negative. F of 2 equal to 3 into 2 square plus 5 into 2 minus 40, which is also less than 0. Now, f of 3 equal to 3 into 3 square plus 5 into 3 minus 40, which is positive, greater than 0. We can take the interval of approximation as this interval 2 and 3, because f of t is negative, f of 2 is negative and f of 3 is positive. We can take the interval of approximation as interval 2, 3. Now, we bisect this interval, that is equal to 2 plus 3 divided by 2, which is taken as x naught. That is equal to 5 by 2 is 2.5, which may be taken as the first approximate root of the exact equation, first approximate root of this equation. Now, we evaluate f of x naught, that is equal to 3 into 2.5 square plus 5 into 2.5 minus 40. F of x naught equal to 3 into 2.5 square plus 5 into 2.5 minus 40, that is equal to 19.375, which is greater than 0, positive. That is, f of 2.5 is greater than 0. Therefore, we can take the next interval of approximation as interval here f of 2.5 is positive and f of 2 is negative in the first step. Therefore, we can take this interval, that is interval 2, 2.5. Now, we bisect this interval, that is x1 equal to 2 plus 2.5 divided by 2, that is 4.5 divided by 2, that is equal to 2.25, which may be taken as the next approximate value of the exact root of the given equation. Now, we evaluate f of x1, that is f of 2.25, that is equal to 3 into 2.25 square plus 5 into 2.25 minus 40, which is again positive. Therefore, we can take the interval of approximation as 2, 2.25, the interval 2, 2.25, because f of 2 is negative, f of 2.25 is positive. There exists a root in this interval. We continue in this manner, we will get the approximate value of the root as 2.136. After 9th or 10th step, we will get the approximate value of the root as x equal to 2.136. This is the bisection method. Now, we shall discuss the second method, that is the method of fixed point iteration. Second method is method of fixed point iteration. In this method, we rewrite the given equation f of x equal to 0 as x equal to phi of x. Using the location theorem, first we find the interval of approximation of the form a b. We put x naught in this equation, in the right hand side of this equation, equation number 1. We will get a better approximation as x 1 equal to phi of x naught. X 1 is a better approximation of the exact root than x naught. Next step, in the next step, we put this x 1 in the same equation, in the right hand side of the same equation, that is x 2 equal to phi of x 1. Then x 3 equal to phi of x 2, etc. In general, x n equal to phi of x n minus 1. After a finite number of steps, we will get the approximate value of the exact root. This is the fixed point iteration method. We just put an approximate value of the root in the right hand side of this equation. We will get the better approximation as x 1 equal to phi of x naught. Then we put this x 1 in the right hand side of this equation and continue in this manner. Now we have to work out a problem. The problem is, starting with x naught equal to 0.21, solve the equation x equal to 0.21 sin 0.5 plus x. Here x naught is given, x naught equal to 0.21. The equation is of the form x equal to phi of x. We put in the right hand side x naught equal to 0.21, that is phi of 0.21 is equal to 0.21 into sin 0.5 plus 0.21. That is equal to 0.122, 0.122, which may be taken as the next approximate root of the given equation, that is x 1 equal to phi of x naught, that is equal to 0.122. Now x 2 is equal to phi of x 1, that is equal to 0.21 into sin 0.5 plus 0.122. That is x 2 is the next approximation of the given equation, that is equal to 0.1224. Now x 3 is equal to phi of x 2, that is phi of 0.1224, that is equal to 0.21 into sin 0.5 plus 0.1224. On simplification, we will get x 3 as 0.12242. Now x 4 is equal to phi of x 3. We will get x 4 as 0.21 into sin 0.5 plus 0.1224, that is equal to approximately equal to 0.12242. In the third and fourth, the values are approximately equal. Therefore, we can say that x equal to 0.12242 is the approximate root of this equation. This is the method of fixed point iteration. Note that for this method, there is a criteria for the convergence of the values of approximate values of the exact root. That is, modulus of phi dash of x should be less than 1 in the interval of approximation. Otherwise, the values do not converge to a limit. This is the convergence criteria. Now, we define the order of convergence. Order of convergence. For an iterative method. An iterative method is said to be of order p of convergence if p is the largest positive real number such that modulus of epsilon n is less than or equal to, strictly less than or equal to, not strictly less than or equal to k times modulus of epsilon n minus 1 raised to p. If this condition holds, we say that the order of convergence is p for the iteration method. Here k is a finite positive constant, epsilon n is equal to x n minus alpha, that is where alpha is the exact root and x n is the approximate root in the nth iteration. Epsilon n minus 1 is equal to x n minus 1 minus alpha, where x n minus 1 is the approximate root of the exact equation, approximate root of the exact root. If this condition holds, we say that the order of convergence is p. If p equal to 1, we say that the order of convergence is linear. If p equal to 2, then the order of convergence is quadratic. For the fixed point iteration, we have x equal to phi of x. Let alpha be the exact root. X n be the approximate root. Let x n be the approximate value of the exact root. Then we can write x n is equal to phi of x n minus 1 by the fixed point iteration method, where x n minus 1 is the approximate value of the exact root in the n minus 1th iteration. Since alpha is the exact root of the given equation, we can write alpha is equal to phi of alpha. This is equation 1. Let it be named as equation 2. Now, we subtract equation 1 from equation 2. We will get x n minus alpha is equal to phi of x n minus 1 minus phi of alpha. By the mean value theorem of differential calculus, we have this right hand side will become, that is phi of x n minus 1 minus phi of alpha can be written as x n minus 1 minus alpha into phi dash of theta, where theta is a constant in between x n minus 1 and alpha, that is x n minus 1 less than theta less than alpha. This is from mean value theorem of differential calculus. Therefore, we can write this expression, that is this third expression, as x n minus 1 alpha is equal to x n minus 1 xn minus alpha is equal to xn minus 1 minus alpha into phi dash of theta. Let k be a constant, or let k be the maximum value of phi dash of x, k be the maximum of phi dash of x in the interval I. Then phi dash of theta, modulus of phi dash of theta is less than 1, that is let k be the maximum means modulus of phi dash of x is less than or equal to k. Therefore, phi dash of theta, that is theta is a number in between xn minus 1 and alpha. Xn minus 1 and alpha are the roots of the given equation. Therefore, we can take this expression as modulus of xn minus alpha. This is named as equation number 4. This fourth equation will become modulus of xn minus alpha is less than or equal to k times modulus of xn minus 1 minus alpha. That is, this is our epsilon n, mod xn minus alpha is epsilon n, which is less than or equal to k times modulus of epsilon n minus 1. On comparing with the expression in the order of convergence, here p is equal to 1. Therefore, we can say that the fixed point iteration method is of order 1, that is fixed point iteration method is order of convergence of the fixed point iteration method is linear. There is a linear convergence for the fixed point iteration method. Let me conclude this session. In this session, we discussed two numerical methods to solve equations of the form f of x equal to 0. The first method is bisection method. In the bisection method, we find out the interval of approximation and bisect the interval. Continue the procedure up to the desired accuracy. In the second method, the method is fixed point iteration method. In the fixed point iteration method, we rewrite the equation f of x equal to 0 as x equal to phi of x. In the right hand side of x equal to phi of x, we put x naught as which is an arbitrary value of the exact root, approximate value of the exact root. Then we evaluated x1 is equal to phi of x naught as a better approximation. Then x2 is equal to phi of x1 is evaluated and continued. After a finite number of steps, we obtain the approximate value of the exact root as the desired accuracy. Thank you for watching this session.